Today's lesson is about defining continuity at a single point. So if you follow these three rules, you can prove that your function is continuous at a point. So the first thing you have to test is the function defined? In other words, at the x value you're trying to prove, does it have a value? And then the function has a limit at the point. So the limit as x approaches 3 of f of x, so the limit exists. Function defined, limit exists, and then the big thing is, well, the limit value has to equal the function value. So in this case, f of 3 would have to equal the limit as x approaches 3. So if those three things exist, we can say that this function is continuous at x equals 3. Okay, so starting out, we have this piecewise function, and we're going to go through this checklist. So we're going to determine if the function is continuous at x equals 2. So first thing, does f of 2 exist? If you notice here, it doesn't exist here, but it is defined here. So at 2, the function value is 1. So it does exist. Okay, does the limit exist? So if we're looking at the limit at this top part of the piecewise function. Okay, when you plug in 2, there's a problem. So let's try factor and cancel. So what is happening at x minus 2? Those cancel. And then you can plug in, so the limit is 4. So the limit at x equals, as x approaches 2, exists. And then at the last thing, does the limit as x approaches 2 equal f of 2? In this case, that is false. So because this last statement is false, the function f is not continuous at x equals 2. So let's think about what is happening in this function. So what we actually have is this linear function that has a hole. And where is the hole? It's at 2. And then here they're saying, well, at 2, the function value is defined at 1. So it's defined here. So this is like y value 1, and up here is the y value 4. So as you can see, because of this hole, the function is not continuous. Okay, in this example, we have a graph, and it's pretty obvious just to look at it, but we're just going to go through this checklist. We're going to test if f is continuous at x equals 0. So first let's check, does f of 0 exist? And it does, it equals 1. Okay, let's check if the limit as we're approaching 0 from the left and the right, that also equals 1. And in this case, because 1 equals 1, the limit and the function value are the same. We are proving that this function f is continuous at the point x equals 0. And as you can see, it's not continuous across its entire domain. Remember, we're only looking at a single point today. Okay, example 3. So we have a new function, and we're going to verify whether f is continuous at x equals 3. So we've got this piecewise function where the domain changes at 3. So let's go through those same steps. First, does the function value exist at 3? So we would have to plug into the top part of the piecewise function. 3 plus 2 is 5. Okay, that exists. Next, we have to test if the limit exists as x approaches 3. Well, for that to exist, we have to test the left and the right. So let's do that. So the limit. Okay, so approaching from the left, we'll use the top function, so that is 5. And then approaching from the right, we'll use the bottom, which is also 5. So then the limit at 3 is 5. So the limit exists at 5. And then, therefore, because the function value equals the limit, therefore, f is continuous at x equals 3. So if you were asked to prove whether a function is continuous or not, you would have to show all of these things to make that proof. Okay, last example. This says find the value of k that makes the following function continuous. So basically we're saying, okay, this will be a continuous function, but what value of k makes it continuous? So what we're doing is on this piecewise function where the domain changes, what we're going to be doing is looking if there is a jump or not. But in this case, we don't want there to be a jump. We want to find the value of k that makes it that there is no jump. In other words, when we plug in 4 for x on the left, so k plus 4 times k minus 3, so that's the left, we want it to equal when you plug in 4 from the right. So k minus 2 times 4. So now we're going to solve for k that makes these equal. And then that will be the value of k that makes the function continuous. Okay, if I multiply on the left, I'll have k squared plus k minus 12. Simplify on the right, I'll have k minus 8. Because I have a quadratic, let's get everything on the left side. So k squared minus 4 equals 0. Then you can just add in square root, or you could think about factoring. So therefore k will equal plus and minus 2. So now you don't have to write this down, but I'm just kind of doing a quick check. So we found this k value. And when the k value is 2, we should not have a jump. It should be continuous. So if you plug in 4 on the left, we'll have, let's see, 6 times negative 1 is negative 6. And if you plug in 4 on the right, you'll have 2 minus 8, which is negative 6. But we also solved that it would work, it would be continuous if x was negative 2, or k was negative 2. So if we plug in 4, let's see, we'll have 2 times negative 5, which is negative 10. Plug it in on the right, we'll have negative 2 minus 2 times 4, which is also negative 10. So it checks. So there is your full video on defining continuity at a point. Good luck with your lesson.